Okay, let's get started. The world, well, it's facing some pretty big challenges with clean water, right? You see these reports, WHO warnings, and the UN even declared this whole decade, 2018 to 2028, as the Water for Sustainable Development decade. It's clearly a massive issue. And, understanding the quality of our water is really step one. So for this deep dive, we've been digging into a really interesting research paper. It's called Comparison of Water Quality Classification Models Using Machine Learning. Our plan is to sort of unpack this paper, see what it tells us about maybe using AI, machine learning, to help monitor water quality.
Exactly. And traditionally monitoring water quality, it's often meant, people going out, collecting samples manually, doing lab work, then maybe some statistical analysis. But this paper, it looks at a more modern way, a data-driven approach using these machine learning algorithms.
Right. And the big question they're tackling, the one we really want to explore, is basically, can machine learning actually do this? Can it classify water quality effectively? And if it can, which specific algorithm, which type, works best, at least according to their study? So jumping right in, what is quality water according to this research? What factors are they looking at?
Well, the paper defines quality using standard measurements, key physical, chemical, and biological factors, stuff environmental scientists typically use. But for this study, probably because of the data they had available, they focus on 4 specific ones.
Okay, 4 parameters. Which ones?
They looked at pH, biochemical oxygen demand, that's BOD, dissolved oxygen, or DO, and electrical conductivity, EC.
Okay, pH, BOD, DO, EC. Why those 4 specifically? What does each one tell us about the water?
Yeah, good question. Each one gives a different piece of the puzzle, right? So
Yeah.
pH, that tells you how acidic or alkaline the water is. Really important because fish, other aquatic life, even our own health, depends on a certain pH range. Think like the WHO suggests 6.5 to 8.5 usually.
Okay, makes sense. What about BOD?
BOD, biochemical oxygen demand, it's basically a measure of organic pollution. It shows how much oxygen is getting used up by microbes breaking down waste. So a high BOD generally means more pollution.
Got it. And DO, dissolved oxygen.
That's kind of the opposite side of the coin. It's the oxygen available in the water. Fish need it to breathe, obviously. So if DO levels are low, it's a sign the water body is stressed, maybe polluted.
Okay, and the last one, EC, electrical conductivity.
Right. EC measures how well water conducts electricity. It acts as a sort of proxy for how much dissolved stuff like salts and minerals is in the water. So together, these 4 give you a pretty decent snapshot: chemical balance, organic waste load, oxygen levels, dissolved solids. It touches on several key health aspects of the water.
All right, so you've got these 4 different numbers, pH, BOD, DO, EC. Each tells a story. But how do you take those 4 numbers and get one simple answer? Is this water good? Is it bad? You can't just juggle 4 values easily. How did the paper approach that?
Yeah, exactly. That's where the idea of a water quality index, a WQI, comes in. It's a tool designed specifically for that, to boil down multiple complex parameters into a single score or category. Makes the data much easier to understand and compare.
Okay, an index. Which specific index did they use?
They used a method called the Weighted Arithmetic Water Quality Index, or WAWQI. Basically combines those 4 parameters, pH, BOD, DO, EC, but it gives more weight, more importance to parameters that have stricter standards or a bigger impact on overall quality. Then it calculates a single index score arithmetically.
Okay, so it weights them based on importance and spits out one number. And that final number, the WAWQI score, tells you the overall quality. How did they categorize it?
Yep. The paper uses that score to classify the water into 5 standard categories. These are the targets the machine learning models will try to predict. So a score of 0 to 25 is excellent. 26 to 50 is good. 51 to 75 is fair.
Okay.
Then 76 to 100 is classified as poor, and anything over 100 is considered unfit for consumption.
Excellent. Good, fair, poor, unfit. Got it. So the AI's job is to look at the raw pH, BOD, DO, EC numbers and decide which of those 5 boxes the water fits into. What data did they actually use to teach the AI? Where did these numbers come from?
They used 2 data sets, both from India, which is great because it's real-world data.
Yeah.
Data set 1 was from the Narmada River. They had monthly measurements of those 4 parameters from 2017 to 2018.
Okay, one river over a year or so.
Right. And data set 2 was bigger. It was historical data combined from several locations across India, spanning from 2003 to 2014. And they mentioned sourcing this data from government websites, so it seems like it's based on actual environmental monitoring efforts.
Yeah, using real river data definitely makes it feel more practical, doesn't it? Not just some theoretical exercise. Okay, so we have the problem. classify water quality into those 5 categories using the WAWQI. We have the real-world data. Now, the tools and the machine learning algorithms. The paper compared 3 different types. Which ones were they?
They picked 3 pretty common classification algorithms: support vector machine, or SVM, decision tree, and naive Bayes. You see these used a lot in machine learning tasks.
Right. For listeners who might have heard these terms, maybe just a quick reminder. How do they work differently, especially for this kind of data?
Sure. Very high level. SVM is generally quite good at finding the best line or boundary to separate different classes of data points, even if the data is complex.
Okay, finding the dividing line.
Yeah. Then the decision tree, well, the name kind of gives it away. It works like a flowchart. It asks a series of questions based on the parameter values, like is the pH above 7, is the BOD below 5, and follows branches down to a final classification. They're often seen as easier to understand, more interpretable.
Like a yes-no path and naive Bayes.
Naive Bayes uses probability. It calculates the probability of the water belonging to each class based on the parameter values. It makes a naive assumption, though it assumes each parameter, pH, BOD, etc., is independent of the others.
Which might not be totally true in the real world, right? These things could influence each other.
Exactly. Environmental factors are often interconnected. But despite that simplification, naive Bayes can sometimes work surprisingly well, and it's computationally quite efficient.
Interesting. And all 3 are what's called supervised learning.
Correct. That just means they learn from data that's already been labeled with the correct answer.
Yeah.
So they're shown examples of pH, BOD, DO, EC values, along with the known WAWQI classification: excellent, good, fair, etc., and they learn the patterns.
Got it. Okay, the moment of truth, the results. How did these algorithms actually do? When they tested them, which one performed the best at classifying the water quality?
So they looked at performance using metrics like balanced accuracy, basically, how often the model got the classification right, taking into account if some classes had more samples than others. They also used something called a confusion matrix to see where the models were making mistakes.
Okay, standard ways to check performance. What did they find on that first data set, the Narmada River data?
On dataset 1, it was actually a tie at the top. Both the SVM and the decision tree models achieved the same accuracy, 87.10%.
87%. Okay, pretty good.
Yeah, not bad at all. The naive Bayes model lagged behind a bit on that dataset, scoring 74.60% accuracy.
Okay, so SVM and decision tree neck and neck on the smaller data set. What about the second one, the larger historical data?
Now this is where it got really interesting, as you said. On dataset 2, the bigger, more diverse historical data, the decision tree model really shone. It achieved an accuracy of 98.50%.
Wow, 98.5. That's a big jump.
Huge jump, and significantly better than the others on this larger data set. SVM came in at 95.63%, and naive Bayes was just slightly behind that at 95.17%.
So decision tree was not only the most accurate on the bigger data set, but substantially so.
Exactly, and the paper also noted it had the fewest misclassifications overall on that data set, so fewer mistakes, higher accuracy.
So synthesizing those results based on their comparison using this specific data, these parameters, and the WAWQI classification, the decision tree came out as the winner.
That's the conclusion, yes. For this specific problem setup, the decision tree algorithm was found to be the most suitable classification model in their tests, especially showing its strength on the larger, more varied dataset.
Okay, so let's bring this back home. Why does this matter to you, listening right now? Why is it important that a decision tree algorithm did a good job here? What's the bigger picture?
Well, I think it really highlights the potential, right? The potential for using machine learning to automate and maybe even improve how we monitor water quality. Imagine you have sensors out there constantly collecting data on pH, BOD, DO, EC. Instead of waiting for someone to manually collect samples, run tests, analyze, you could have a trained model, like this decision tree, giving you a near real-time classification.
So faster alerts if something goes wrong.
Potentially, yes. If there's a pollution event or a sudden drop in quality, the system could flag it almost instantly. That could lead to much faster responses, faster action to fix the problem compared to traditional methods.
And the fact it was a decision tree, which you said is more interpretable, does that matter?
I think it does. It suggests you might not need a super complex black box AI model that nobody understands to get really high accuracy here. Having a model you can somewhat understand, like a flowchart, could be really valuable for, say, regulatory agencies or water managers who need to trust and explain the system's decisions. It's about using data smartly to get insights, quickly and reliably.
Okay, so to quickly recap this deep dive, we looked at this research paper comparing machine learning models for water quality classification using real Indian River data, 4 key parameters, and the weighted arithmetic water quality index. The study found that, out of SVM, naive Bayes, and decision tree, the decision tree algorithm proved to be the most effective, especially hitting that impressive 98.5% accuracy on the larger dataset.
Right. And it makes you think, doesn't it? The paper itself mentions directions for future work. Things like using even larger data sets, maybe more diverse data from different regions or types of water bodies, and also identifying other parameters beyond just the 4 they used. Which brings up a final thought for you to chew on. Given how incredibly complex water systems are in reality, what other factors do you think are truly critical for judging water quality? Things maybe not easily measured by simple sensors, like maybe certain specific chemicals or biological indicators. And how would trying to include that kind of data challenge these machine learning models? Or maybe even lead to discovering better models or different approaches? It really underscores that while these results are promising, capturing the full picture of water health is still a huge ongoing challenge.